Okay. All right. Welcome, everybody. Thank you for coming to our interdisciplinary seminars. It's a pleasure to have here today Dr. Vijaya Kumar from Carnegie Mellon, where he actually got his PhD from as well. And he's been there since 1982. He's now professor and associate dean. I didn't see that. Associate dean in the College of Engineering. He also served as the associate head as well as the acting head of the ECE department. His research topics include pattern recognition with all sorts of applications, particularly in biometrics, and coding and signal processing for data storage systems and digital communications. He's authored and co-authored over 500 technical papers, 15 books. Goodness gracious.
No. 15 book chapters.
No, 15 book chapters. and one book on correlation pattern recognition. He served as a topical editor for Applied Optics and associate editor for the IEEE Information Forensics and Security. He's an IEEE fellow and a fellow of SPIE, a fellow of Optical Society of America, and a fellow of IAPR, which is the International Association of Pattern Recognition. It's a pleasure to have him here, and thank you for coming. It's a pleasure to have you.
Thank you very much. Thank you all for coming. As Hamid said, I've been working in the pattern recognition area for many, many years, all at Carnegie Mellon since 1982. Most of the work we did for the first, I would say, 20 years was in applications like automatic target recognition, looking for tanks and trucks and other kinds of things in interesting scenes. But it turns out over the last 10 years, most of our work has switched to biometrics. The problems are very similar, so we bring the same tools that we found very successful in ATR applications to biometrics. So today's talk over the next 5 hours, is that? No, next hour will be to talk about, what are these methods and how we are using them. And what I'm going to talk about is actually just give you high-level details, high-level stuff. And the details, you have to go read the papers if you're interested. I won't have time to get into much of the details. I'll send Hamid my slides, so if anybody is interested, you can get it from him afterwards. Okay. So obviously, this work is not possible unless a lot of students helped along the way. So an acknowledgement of former and current students that have helped me, and also the funding agencies that supported this work. So I'll start first by describing correlation filters. The concept is very simple. Once I explain it, it'll look like it's so trivial. How can it work? But hopefully, I'll convince you that it still has lots of power by showing you the results that we get with these things. And I'll explain the basics of correlation filters, but then spend more time on showing how we have used it very successfully for face recognition, iris recognition. And then if we have time, there are two other twists. One is called cancellability. That is, if you're going to use biometrics, like you use your credit card, if you lose your credit card, it should be canceled and a new credit card should be issued. But if you're using your face as your biometric, what happens when your biometric template is stolen? Okay, now we have only one face. So what do we do? So cancellability is an important issue. And encryption, that is, if you have a secret key for whatever reason, secret keys are used everywhere. Normal thinking is that you match the biometrics, that's how you authenticate the person, and you release the key. But that's a two-step process, and an attacker can get in the middle and just spoof the output from the biometric matcher as a yes and release the key. So it's better if you can combine the keys directly into the biometric. It's called biometric key binding.
Excuse me, sir.
Yeah?
We lost your content whenever you switched over. Somehow or another.
Did I do something?
Are you talking about?
There we go.
Are you okay? Okay. So we're going to talk about encryption, how to combine a biometric modality with a secret key in a one-stage process. So I hope to get through all those slides, but I have several slides, but most of them are visual, so we should be able to get through this pretty quickly. So let me just define, or at least invoke the standard definition of biometrics. Biometrics is something that you can measure and something that is unique to a person, whether it's a physical characteristic or a behavioral characteristic, and but we can use it to verify the identity of a person. There are a lot more precise definitions, but for our purpose, that's good enough. Okay. And why is it interesting? Because it is, at least initially, people thought it's a way to replace things like passwords or tokens. Passwords people forget. RFID token to access some place, you can lose them. And hopefully biometrics is something that stays with you and you don't lose it. Okay, so that was how interest in biometrics got started. There are lots of modalities for biometrics, face images, palm prints, fingerprints, iris, let me see if so this is iris image, oops, and this is a retinal scan. This is a speaker recognizing somebody from the way they speak, recognizing somebody from the way they walk, gait pattern. Of course, dental X-rays, not quite friendly biometrics, are invasive. Some of these biometric modalities are more invasive or require more cooperation than others. Earlobes. You won't think of ears as very discriminatory, but they are. And in fact, many countries require for passport photos that ears are visible. They don't want you to look straight at the camera, slightly off angle, so that one of the ears is visible. Handwriting. Handwriting is the oldest form. Signature is the oldest form of biometrics, but it has its own complications. Matching them is not easy, and it's used in many places. Right now, Hajj pilgrims in Saudi Arabia, when they get their iris images, and as they go through various lines, they are checked to make sure that somebody else isn't substituting for them, that the same person is going through. There are attempts to use fingerprints at the cash registers in grocery stores. Have not been terribly successful yet, for a variety of other reasons, not the technology really. Iris recognition is used. Yeah.
I guess in Saudi Arabia they use iris because they can't use the face. Right?
I want to be politically correct today. Okay. We won't go there. Okay. I have lots of stories to tell you about it separately. Smart guns. Guns that won't fire unless the fingerprints match, so that your gun only you can fire, not somebody else. Iris recognition for frequent flyer travelers. People that fly a lot, if you can get your iris template into the system, now you can cut all the long lines and go through and get checked through that quickly. Not many airports have it, but some do. I'll talk more about all of these when I talk about iris recognition. So just for some terminology, we use the terminology verification to mean one-to-one matching. Like you go to your ATM machine, you slide your card and you stand in front of the camera, and the camera takes your face image and has to match what's on the, essentially either stored on the card or stored in some central server. But all it is trying to do is, are you the person who you claim to be? Or are you an imposter? So that's just a one-to-one matching. But there are applications, many applications, where you have to do one-to-n matching. Somebody's image is collected, and you have a watch list of people you're looking for. And you have to say, is this face one of those n faces? Okay. We'll use loosely the term recognition to mean both of them. Because generally, if you can do well on one of them, you do well on the other. Not always true. Sometimes verification, even though it's one-to-one matching, is harder than doing identification. Because in verification, you have a threshold. When the score is above the threshold, you say it's a match, otherwise it's not a match. And suppose it's a dimly lit room and the face image is not a good face image. You may not reach the threshold. But when you're trying to compare that dimly lit face image against 100 others, all the scores go down. And when all the scores go down, the right one may still be the correct answer that you get. So it's not automatic that 1 to n is harder than 1 to 1. It depends on how you use it. So what is the problem? It's a match. All you're trying to do is matching. Well, the problem is what we call face image is not the same all the time. People's expressions, pose, illumination, light levels in the room, they all change the values of the pixels you have for the image. And although the computer, of course, the algorithm is trying to do is match the pixel values. And this is actually highly, cropped face images with no background whatsoever. This is a very nice set of images. But the reality is there will be background in the scene, not just face by itself. And if it's iris, people close their eyelids, eyelashes. They won't be looking straight at the camera. They'll be looking somewhat off axis. All these change the image. When the image changes, matching is difficult. And so it's the variability in these image patterns that's what is challenging. If the image that you collected at the time of enrollment is identical to the image you get at the time of testing, this is an easy problem. There's not much to do. It is the reality that it's hardly ever the case that the two are the same. And so it's a standard pattern recognition problem. You're dealing with variability within one class or one subject and discrimination between subjects. You can design systems that accept all kinds of variability, but then they will accept the imposters also as authentics. So where do you draw these boundaries to separate different people and at the same time allow variations within one class? So we have the same problem in automatic target recognition. When you take an image of a vehicle from a distance, it can appear very differently depending on the viewpoint and the time of the day, how long the tank has been running around. If it's an infrared image, it will be brighter if it's been used for a long time, and it will look dimmer if it's been sitting there for a long time. But it's still the same object, and you need to be able to recognize it as the same object and differentiate it from all the other vehicles. Okay, the same kind of problem. So we have had lots of success in using the basic idea of correlation. And so let me just briefly talk about what is correlation and then how we use it in face and iris and other places. Correlation at the very core is very simple. You have two images. We're calling R of XY as the template image, or you can call it a reference if you want. S is the query image or the test image. And what you do is you simply take the two images and do an inner product between them. That gives you just one number. If these two are perfectly aligned and registered, you should get a high number because positive numbers will multiply positive and negative numbers will multiply negative. Why negative? Maybe because I subtracted the mean from both images. Okay? You'll get a big inner product. But the two images may not be aligned because the enrolled image was collected in a nice maybe studio setting, and the test image is wherever it's being collected. There's no guarantee it will be centered. So now you have to try for all possible shifts. This is particularly true in ATR applications because the tank, you don't know where it is in the scene. And in fact, there can be multiple tanks, multiple trucks in a given scene. So you don't even know how many of them are there, where they are. So you have to try for all possible shifts, these inner products. And that's what I wrote integrals, but you can think of them as double summations. It doesn't have to be integrals. Okay? I'm old-fashioned. I still write integrals. Okay. So the result is a correlation as a function of the shift between these two probe and gallery images. And if the image contains what you're looking for, an authentic image, then you will get a large value at the right shift and small values for all the other shifts. If the query image is from an impostor, somebody else trying to get in as you, if this template was carefully chosen, RFXY was carefully constructed, you should not get large values anywhere. That's the idea. So the key to the whole thing is figuring out what this template should be. If the template is very simple, which is just whatever you collected at the time of enrollment, it will work only when the test image is almost identical to the enrolled image. You put any differences like rotations, a little bit of scale difference, it won't work, okay? Which is the real problem. Okay? So there's a lot of work that happened over the last 25 years on how to design these templates. These are not simple matched filters. Simple matched filters don't work. Okay? So plug for my book. We wrote a book on how to design these things. So that's the only book I wrote, okay, not 15 books. Okay, so I will talk about just one approach. There are easily 10 or 12 different ways of designing. In fact, those templates, we're going to call them correlation filters from now on. Why filters? Because all these are actually implemented. This equation that you just saw is most efficiently implemented in frequency domain. This is just like convolution, except you don't flip the thing. It's correlation. So you can implement this by taking the two images, doing 2D Fourier transforms on both of them, multiplying the two arrays point by point, and then doing an inverse 2D Fourier transform. That's much more efficient than doing this directly as it appears. One is, if it's got n pixels, you'll need n square operations. If you do it that way, this way, if you use FFTs, you will need some 3 times n times log to the 2 of n operations. And especially when n is like, even for a small image like a 64 by 64 image, n is 4,000. So the difference is huge. So you should never be implementing it directly. You should always be going via FFTs for these things. And that's why they're called filters, because all the processing is done in the frequency domain. These filters are not like low-pass filters or high-pass filters where we're trying to pick some frequencies and suppress some other frequencies. In fact, for these filters, phase is the most important thing, not magnitude. I can take a correlation filter and change the magnitude of the filter to 1, set it, and just not pay attention to the magnitude. It still will work reasonably well, not as well as the original one. Okay? But if I change the phases, it won't work at all. It's the important thing for pattern recognition is matching the phases, not matching the magnitudes. Okay. So how do we design this template? So I'll give you just very quickly a general idea. Let's say we're trying to design a filter to recognize this face or this person's faces. Let's say I have 3 images of this person. During the enrollment, I collect 3 images. It's a 2 by 2 image. I do a 2-dimensional Fourier transform. Okay? It's a d by d pixels or d square pixels. I string them out into a column vector. Okay? And if I have 3 images, I make 3 column vectors. So that's a matrix X, big X. I'm trying to find the filter that we call capital H here. That's in frequency domain, spatial frequency domain, because these are Fourier transforms of images. It's a d by d matrix, and it also has a corresponding vector small h. Again, scanning it from left to right, top to bottom, convert it into a column vector. So one of the things we're going to ask for, at the training time, these are all centered images. The training, I can center them. It's the testing time, I don't know where the image is. So these are centered, and what I want is when this is correlated using that filter H, I want at the center of the correlation output all these images to give me, for example, 1, let's say. So even though maybe this is 3 different expressions, I want the inner product of them all to be equal. Okay? So that way correlation output at the center is going to be 1. But 1 is arbitrary. I could have made it 10 or 100, it doesn't matter. But the more important thing is what I do next. I also insist that the rest of the correlation plane be as small as possible. Center has to be 1, the rest has to be, ideally I want it to be 0 so that this 1 stands out, but I can't. I can't get zeros to come out when I put a non-zero thing into a linear system. Okay? So, I mean, I'll skip the math, but you can write an expression for the energy in the correlation output. So instead of making all of them small individually, I'll simply say the energy in the correlation plane should be as small as possible, sum of squares of all those pixels. It turns out you can use simple things like Parseval's theorem and all that, and you can get actually a quadratic expression for the energy in terms of the filter vector that you're trying to design and the average power spectrum of the training images. So you take all your training images, in our example we have 3, take the Fourier transforms, take the magnitude squares and average them, you get the average power spectrum, and take that and write it along the diagonal of this diagonal matrix D. And you can easily solve this, a very simple optimization problem. Minimize this subject to the linear constraints we had on the previous page, these constraints. And it's a very closed form answer you can get for what the filter should be. And once you get this filter, it's a vector, but you can now put it back as a 2-dimensional array, and that's your correlation filter. And this is simply called MACE filter, minimum average correlation energy filter. This is about 20 years old. Since then, lots of other advances have been made, and I'm not covering them. Yes?
You mentioned how people have different expressions when their picture is being taken. Have people tried, researchers tried to look at, let's say, manifolds to represent different twists in the image?
Yeah, people have been using manifold-based approximations to not just expressions, even illuminations and poses, different orientations of the face, and they use local linear embedding and all these other approaches. And so the one advantage of these is these are all in linear subspace formulations, so you get nice closed form answers. Once you go off of that, you have to, there is some seat of the pants that you have to do. It's not as clean as some of the answers you will get here. But it's clear that if you take the set of face images with, let's say, expressions, it is not a subspace. We know that. It's actually better approximated by some manifold. So these are not good approximations, but lead to very efficient solutions. Better approximations would be manifold-based ones. Exactly. Okay. So what does this MACE filter look like? Well, if I showed it to you in frequency domain, it would look like a bunch of random things, where you have no intuition to look at frequency domain, particularly when I say it's the phase that is important, right? If I show you a phase of a filter, it doesn't mean anything. So we took the inverse Fourier transform of that filter, and that's what this looks like for that person. All I can say is, yeah, it does have some features that look like face, right? Some eyes are there, some nose is there. It seems like some areas are brighter than others. But the bottom line is, how does it work? Okay. So this is how we're going to use it. Basically, I'll talk first about face recognition, then I'll show you how you use it in iris. So the idea is you take training images, you design the filter like we just talked about. As I said, I talked about only one type of filter design. There are at least 12 different types of filter designs. Okay? So MACE is not the way to go. Let me just put it that way. There are much better ways to do it now. MACE is the easiest to explain. That's why I showed you that. So you design the filter, and that's what you store on your smart card. That's what you take around with you. Next time you go to your ATM machine, you stand in front of the camera and give an image. It should take the FFT, multiply with what is stored on your card, and do an inverse transform. If it's you, it should produce a peak. It doesn't have to be in the center, because if you centered your face perfectly in the field of view, it will be in the center. But this is a linear filter. If the input gets shifted, the output gets shifted exactly by the same way. It's a LTI, linear shift invariant filter. Okay? So you don't have to center the input. Okay? So it can be anywhere, and you will, if you get a peak, yes, it's the right person. Otherwise, you'll get something like the no match output. It's the wrong person. Yes.
In the quadratic form that you had, is your central matrix always positive definite?
The D matrix?
Yes.
Yeah, because the D matrix is made up, it's a diagonal matrix, and what's along the diagonal are the average of the magnitude squares of the Fourier transforms of the images. So at worst they will be zeros, but we fix that by adding a small epsilon regularization term. We make sure it's invertible.
Okay.
Yes, and it's positive. And that's why this actually is very easy to do, because this big D matrix is diagonal. So the only real inverse you have to compute is this one, x plus D inverse x, and the size of this is the number of training images, not the number of pixels. So if I'm using only 3 training images, this is a 3 by 3 matrix. Whereas even though D for a 64 by 64 image is a 4096 by 4096 diagonal matrix. But that's diagonal. Inversion is easy. So one way we quantify how sharp this peak is compared to the background, there is a metric called peak to side lobe ratio. We measure how high is the peak compared to the standard deviation of the values around it, and we look at that number to say, is this authentic or impostor? So let me just show you a bunch of results first. So CMU many years ago collected this database called PI database. PI stands for Pose, Illuminations, Expressions. So face images where poses, illuminations, expressions were controlled. 65 subjects, and this is one subject's face under 21 different illuminations. In particular, pay attention to number 3, 7, and 16, because those are the 3 we are going to use as training images. This is the one with the left part of the face in shadow, no shadow, and right part of the face in shadow. Yeah?
Is this database publicly available?
Oh, it's been available for a long time. So, and in fact, there is a newer database called MultiPy, which has a lot more subjects, 330 subjects. That's also publicly available. All you have to do is send a hard disk because it's several hundred gigabytes of data. So we are going to train the filter using just number 3, 7, 16 as our example images. And so we got a filter, and we're testing it for the same person's image number 10, a different illumination. Here is the correlation output you get. And this is just a cross-section view, and this is a top-down view. You see a bright spot there. But more importantly, the match score, or the peak to side lobe ratio, is about 41 in this case. It's a very distinctive peak. Now, the filter stayed the same, but the input was, we covered part of the image, obscured. You can still see a very nice peak. It's not as good as before because the peak to side lobe ratio is only 30, not 41. But if I give this as image to most of the commercial face recognition systems, they'll throw it back because they say we can't see the 2 eyes. They have to see the 2 eyes first, because then they do eye detection, put crosshairs, and then they adjust the image, and that's how they go. Then they calculate features, and then they will match the features and do all kinds of interesting things. But not seeing the eyes is a non-starter in most of these images. But correlation filter looks at all the pixels. No particular pixel is critical. So this is what we call graceful degradation. I mean, it degrades, obviously. If you keep blocking off more and more, this thing will start diminishing. But, it's graceful. No particular part is critical. Okay? So it's because it's a global method. It's looking at all of them. It's not paying attention to just local regions. What if it is not centered? So we deliberately moved it down, and you can see the peak is not at the center anymore. And this is no problem either, because what do we do when we get this output? First thing we do is go look for where is the biggest value, and then we calculate PSR with respect to it. The fact that the biggest value is not at the center is not a problem.
In these images, are you still keeping the same pixel set? You're just making you're just
Yeah,
putting
the image
making
is still whatever size
Oh,
it was.
okay.
These were just
You're
zeros.
just zeros there.
Yeah.
Okay.
Because the FFTs still have to be of the same size for me
same
to be able to multiply them. I can't take a smaller size FFT and multiply it by a bigger. So I have to zero pad
Okay.
if you give me a smaller image. Okay. Somebody else's filter. So same input image, but we test it against somebody else's filter. This is the output you get. Of course, there is a peak somewhere. Peak meaning the highest value. So you go find the highest value and calculate the peak to side lobe ratio. It's about 5 in this case, as opposed to 40 or 30 we say. So typically for these size images, which are like 100 by 100 images, we will put a PSR threshold of about somewhere between 10 and 15. If it's above 15, we say it's an authentic, and below 10, imposter. In between, get another image, something like that. Okay, so just a high-level summary of what you have seen so far is that correlation filters, are because they're filters. They're linear shift invariant filters. First thing you learn in signals and systems course, I guess. There is no need to center the image. So I don't need a face detector to go center the image first, and then I calculate the features to do the matching. The image can be anywhere in the scene. I don't need to figure out where it is. Part of doing this is figuring out where it is. Right? That's why it works well in ATR applications, because I don't know where the objects are. If there are 3 tanks, I'll get 3 peaks corresponding to it, and I play this filter against it. And that's how I know where they are. Okay? So if you see most of the biometrics literature, they work really hard to center the face first. If you can't do it well, or if you do it but you're off by a few pixels, the features change, the features you compute, and they won't match anymore. Here we don't have to center it. It's part of the matching process. It's graceful degradation. It can handle multiple appearances. In biometrics, it's not a big advantage because most of the time there's only one person there. But if you are, looking for 3 different people in a photograph, maybe you'll get 3 peaks if you can do that. Closed form solutions. It won't quite work when we go to manifold representations, but in the subspace representations, we do have closed form. So these can be, designing them is very quick. We don't need, lots of optimization programs to work on this. Okay, so we took this to, NIST had a thing called Face Recognition Grand Challenge a few years ago, about 5 years ago. So we submitted our correlation filter-based method. So these are some statistics about it. So they had a generic training set. They had about 12,000 images from 220 subjects that you could use to train your filter. And then you give them the filters, and what they do is they had 2 sets of tests, gallery set, probe set. The terminology used in this community is different from what you hear in pattern recognition. Gallery is like training set, enrollment set. Probe is like test set or verification test, verification set. So these are the same people, 466 people, but images collected under different conditions. These are from control, like a studio type of setting images. These are more outdoor type of images. Okay, I'll show you some. And the baseline method that NIST supplied, which was using PCA, Principal Component Analysis, Eigenfaces, whatever it's called, it gave they wanted a 0.1% or 1 in 1,000 false accept rate, an imposter getting in as an authentic. Okay? And then they said, what is the true verification rate? How many people are correctly verified at this level? PCA gave 12%, not very good. I mean, the higher this number is, the better we are. So here are some images of what they call gallery images. For those working in face recognition, this is Professor Kevin Boyer of Notre Dame. He becomes the face of face recognition research because a lot of databases come out of Notre Dame. And for privacy reasons, he is the volunteer whose face always appears in publications. I mean, you name it. Every face recognition paper has his image there. So these are images collected in the corridors, and there are even some outside the buildings. Those are the uncontrolled images. So when we submitted, so these are our results. This is verification rate. This is the baseline, 0.12%, and our method, actually variations in our method. So this is the basic method. These are what are called kernel versions, nonlinear adaptations of the basic method. So we reached up to 82.4%. At that time, we were number one. Okay, compared to even other methods like commercial methods that were out there. Since then, other people have improved it. Now the state of the art is people have reached 91% on this thing. Okay? We have not been able to improve this. Maybe we got up to 85, 86%. That's how far we got. So while I'm in the face recognition, I also wanted to just briefly show these results where the problem is many times you have good quality training images, or what we call high resolution training images. But the test time, the resolutions of these images are crummy, very low. How do you match the two? There are two approaches at least. One is make the high resolution training images into low resolution ones and build filters or whatever on that and match. Or take the low resolution test images, apply super resolution methods and match there. Okay? But the problem with most super resolution methods are they are aiming at reconstruction of these images to make the images look good. That's not what we're interested in. We are interested in recognition, not restoration or reconstruction. Different objectives. So how do we get good results? Yeah, you have a question?
Yeah. So the correlation filters you showed were shift invariant, which was clear.
Yeah.
How did you adjust for the scale of the images?
No, we did not adjust for the scale in this case, or even rotation we did not. What you have to do is, there are two approaches at least. One is you show training images of different scales. You artificially change the scale of the image or rotate the image, and they become part of the training images from which the filter is designed. A better method would be to use what are called circular harmonic functions for rotations and Mellin radial harmonic functions for scale. And we actually published papers on IEEE transactions on image processing on both these methods. I can send you references. Okay, so like in this video surveillance example, I mean, you can hardly see the face of that person. There are hardly any pixels. How can you match in those cases? So super resolution is one approach to go from low resolution to high resolution. Basic idea is Tikhonov Super-Resolution is you have a low resolution input. You're trying to get the high resolution original. And in our case, we're assuming we know the mapping from high resolution to low resolution or the blurring operator. This may not always be the case. In uncontrolled situations, we may not know what B is. So one seat of the pants solution is to try lots of B's, reasonable B's. But in this experiment, we assumed what B is. So the idea is to get the X so that BX is as close to the low resolution input as possible. But if you do only this, you'll get a very unsmooth result. So you throw in this regularization factor that basically says the edge information or whatever, gradient, whatever. L basically is measuring the how much edge information there is. And you want to minimize that too. And there is an alpha that weights the two. This is the standard super resolution approach. I mean, there are variations on this. This is not the only way. So the twist we added is we added a third term to this whole thing based on features. So for example, if you are going to use, let's say, Fisher faces, it doesn't have to be Fisher faces. It could be eigenfaces or something else. It just has to be linear in our formulation. You try to match, you try to find the X whose features also match the stored features, not just the low resolution input. Okay? So surprisingly, this was not, as far as we could tell, this was not attempted even before. It's a very simple idea to add the features, because that's what we end up using for recognition at the end of the day. So we tested it on this multi-pi database that I talked about, 330 subjects. And in this case, it's frontal views, neutral expressions. People are not smiling or anything like this, even though the database has all those expressions too. Only changes here are illuminations. Okay? So in the interest of time, I'm going to skip these details, but just get to the results here. So these are the original multi-pi images. When I say high resolution in my experiments, they're 24 by 24 pixel images. Okay? I'll explain why that is the case. So the low resolution image I'm going to use is 6 by 6 pixels. So we're trying to match these images to those images. Okay. So why 24 by 24? We actually experimented first matching what is the identification accuracy. This is what called rank 1 identification accuracy. What is the percentage of correctly identified people out of the 337 or whatever we have in the database. You can see once the size of the pixels, this is image 24 by 24 image, 32 by 32, 48, 64 by 64. Performance didn't change much past 24 by 24. So we said it's not fair to start with 64 by 64 as high resolution and show good results with 32 by 32, because you would get good results whether you use super resolution or not. Okay? So we started with 24 by 24 and show good results using smaller ones.
This curve is for human observers?
No, this is the Fisher-Faces algorithm. There's no humans in any of this thing. I don't know how humans would... my suspicion is humans are not going to recognize these 6 by 6 images. And it's not 1 or 2, it's 337 subjects we're talking about here. If anybody is interested in how humans do well on face recognition, there's a beautiful paper by Pawan Sinha in Proceedings of IEEE in 2006, I think. He goes through 11 or 12 different examples, putting George Bush's face on Bill Clinton's body and changing the hairstyle. We use lots of other cues. And if you see, we're very careful in all these experiments to crop the face to just the face. We don't use cues like hair or ears or anything else, because humans actually use a lot of that other information to do a great job of recognition. But if you just show only these kinds of things, humans are not very good, not as good as the machines. Again, it also depends on how many, is this celebrity face, or is this a relative's face, or is it somebody who you have never seen? Those matter a lot. Okay, so here are the results. This is again rank 1 identification accuracy. Higher is better. If you just use simple interpolation on the low resolution images, like bilinear, bicubic, or even Tikhonov Super-Resolution, the results are like 15%, rank 1 ID accuracy. If you just stayed at the full 24 by 24 resolution for both testing and training, you get 87%. Okay? If you just stayed at low resolution, 6 by 6, this is a factor of 4, you get 47%. By using these, what we call S-square, simultaneous super-resolution recognition. So that's what S-square, R-square stands for. These are slightly different flavors of it. We're able to get to 73% on this thing. Okay, I spent much more time than I had planned on face. Let me go through iris very quickly. Any questions before we switch topics here? Yeah.
So, since you've seen lots of image processing algorithms, so in all the different image processing algorithms, there's some misses which you don't identify properly. Is there any non-empty intersection in the faces which miss identification and all this?
Oh, we do have misidentification. That's why our rank 1
So,
ID.
are there any common features among faces which get missed?
Good question, but I don't know the answer. Many times We do try to take a look at where the methods fail. They fail for a variety of reasons. Things being occluded, illumination changes, small expression differences, and many of them come together. So it's very difficult to separate them and say this is what is causing the problem. If I had to pick one as the most challenging problem, it's the pose. Illumination is not as big a problem. I think we can solve it pretty well. Expressions are a problem, but there is not a huge dynamic unless you are a drama major or most people don't have dramatic changes in their facial appearance because of expressions. But pose, you can have a wide variation in how the images appear. That's why mostly they fail, because of pose. Okay, so I don't know if you know about the history of iris recognition, but nearly, I guess, 25 years ago, a couple of surgeons, eye surgeons, while they were doing eye surgeries, realized that this iris pattern, that's the thing between your pupil and the sclera, the white part, in between this part is distinctive for people. So they actually filed a patent to use, these are eye surgeons, Flom and Saphir. They filed a patent. The patent expired a few years ago. But it really became a popular biometric modality when John Daugman of Cambridge published the main paper in 1991 showing how to take that image and actually do iris recognition. Okay? So I'll talk briefly about it, but I will also show correlation filters can be used. The bottom line is correlation filters can be used as long as it's an image that you're trying to match. It doesn't care whether it's tanks or faces, fingerprints. So we don't use it for speaker matching, but we can use it for any images. So I don't know if you've seen this picture before. So this is a very famous cover from many years ago on National Geographic of an Afghan girl during when Russia and the USSR and Afghan, there was fighting going on. So the National Geographic magazine photographer took this beautiful picture, and they wanted to locate her 14 years later. They went back to look for her, and there were several candidates that came forward as the person. Okay? Now, because the photographer never kept record of who it was, he just took a random picture, beautiful picture. So one of the things that they asked around, and they did all kinds of analysis, but one of the key pieces of evidence is matching the iris in this beautiful photograph, because this is one of the distinctive parts of this photograph, to the iris of this real person. And based on that, they established that she is the same person as this 14 years later. Okay, so this was a very famous example of iris recognition at work. Not so popular example of iris recognition at work is how it is used in UAE. UAE airport has an iris recognition system. So apparently they expel people from UAE for violating their laws. When they expel, they collect the iris images. So when people try to get back into the country, they match the iris images of the incoming people against their database. And they claim it works beautifully. My only problem is I don't know whether it works beautifully or not, because if somebody who came through, they're not going to say, your system failed, I just got it. So I don't know. It's not a true scientific experiment, but it's used. Okay. It's also used in other places, like India has a huge program now. They're starting called Unique ID, UID. The plan is 1 billion people are going to have identification systems based on biometrics, fingerprint and iris. Okay, and it's a huge project, and we're all waiting to see how well it's going to work. But iris is one of the modalities that's being used. So how is the matching being done in iris? So you start with an eye image. You have to find the inner boundary and outer boundary of the iris. Then this iris region is mapped into a rectangular polar coordinates. It's converted into r theta, theta being the angle, r being the radius. And then you apply Gabor wavelets. Gabor wavelets are simple, they have a Gaussian feature, and then they have frequency variation in them, and these Gabors could be wider or narrower, and they can have orientation in 2D. You can vary lots of parameters, and you put them at different places. Every inner product of the polar coordinate transformed iris and a Gabor wavelet gives you one complex number to come out, inner product. And you see where the complex number falls in the complex plane. If it falls in the first quadrant, you say that is 0, 0. Second quadrant, 0, 1, 1, 0, 1, 1. You get 2 bits of information. So by changing parameters of the Gabor wavelet and changing the places where you put this Gabor wavelet, you try 1024 of those variations, you get a 2048-bit iris code. So we all will have a 2048-bit code associated with us, or at least one iris. This iris is different from this iris. They don't match at all. Okay, there is no commonality. Even the twins, identical twins, don't have identical iris codes, iris patterns. Okay? So the story is when, so you have your iris pattern, collect iris code made at the time of enrollment. When you go to the testing, again, we take your iris image and create the code and compare the Hamming distance between the collected code to the stored code. If they are from two different people, half of the bits will match, half will be different, so normalized Hamming distance will be half. If they are identical images, normalized Hamming distance should be 0 or small. And that's but of course there is a distribution. They're not 0 and they're not half, but the overlap is very small. So that was the original Daugman idea. But we also can use correlation filters. It's just a matter of matching the 2 unwrapped images. So we did that. And part of, maybe I'll skip this part actually. So if you look at parts of this unwrapped image, these are 2 images of the same person at different times. You can see different parts of this iris move differently. They don't all move the same way. It's not like, it's because these are all individual muscles that are moving your iris and eyelids. So we designed a graphical model, Bayesian graphical model that actually captures these nonlinear deformations. And also this part is your upper eyelid when you convert it into the polar coordinate system. And so the information here is not reliable. There is no iris information. It's covered by the eyelid. So we designed so there is the eyelid, and we designed a probabilistic model that essentially looks at the stored pattern and the incoming pattern, and it tries to estimate how much occlusion is there, how much nonlinear deformation is there before it puts out a score value. And so this basically is the unwrapped polar coordinate version of the iris. We divide it into patches, and we correlate each patch from the queried iris image to each corresponding patch in the stored iris image. And these little arrows you see show what is the relative movement between the query and the stored one, and the length of those arrows. So the direction is in what direction did they move, and the length is how much did they move. Okay? So you can use all this information, and also you can estimate which parts are occluded. Right? If some part is occluded, when you do the correlation, you're going to get small peak, and you can use that information to estimate which parts are occluded. So all these go into essentially a Bayesian graphical model. Sorry, I'm actually rushing through this. If you really want the details, you have to read the IEEE PAMI paper we have on this stuff. So again, punchline is we submitted this to the NIST, another evaluation called Iris Challenge Evaluation. It had 2 experiments, left eye versus left eye and right eye versus right eye. Okay? and it's based on data collected at Notre Dame. I don't know if this is Kevin Boyer's iris or not, because I don't see the full face. But there are that many subjects, 120 subjects roughly. So here are the results. These are different participants. Some of the participants you're not seeing because their performances were low in this graph. What you are seeing is the verification rate. That means the correct verification of an authentic when the false accept rate is at 0.1%. Okay. The two colors, the red is right eye versus right eye, blue is left eye versus left eye. This actually starts at 0.95, 95% verification rate. That's 100% verification rate. So if you look at all the way, the best red bar is Sajam, big company that works in biometrics area. Second best is CMU. And the best blue bar is Iritech. This is a Korean company. And the second best is CMU. So we came, and these differences are, this is 99%, 98%, 99%, 99.5%. So iris recognition works very well, and if the challenge is really getting good quality iris image. If you're close enough to the sensor, you can get good quality image. But if you're far from it, you don't get good quality. That is the challenge, really. Now, I got two other topics I can finish in maybe 5-10 minutes.
Sure.
Is that okay?
5 minutes, yeah. We're going to get off.
One quick question
Yeah.
on this. Why is there the difference between the right eye?
Yeah, I don't know. I asked them the same thing. I don't have any reason to say why. Oh, but this is not only here. I've seen other experiments also where left eye recognition rates, even though they're also very good, are slightly lower than the right eye versus right eye. Some people say that's because people are used to putting their, they use the right hand more often. So when they provide the image, somehow they're providing better quality. Maybe they're more orthogonal to the camera or something like that. I don't know if that's the case. That's the reason. There isn't any biology-based reason that it makes sense there.
What about the quality of the pictures that are taken?
They were all taken at the same time, same camera. But that may be, maybe the person taking the picture, some undergraduate student who's being paid $5 an hour, all these things. So I don't know.
$5? Why so much?
We'll pay $7 if you come to CMU. Okay, so let me talk about the other two because I think they are interesting, cancellability and encryption. So if you're going to use your biometrics for accessing your bank account, ATM machine, what happens if you lose it? If it's credit card, they will issue a new credit card with a new number. But how do we do that with biometrics, especially when there is only one face? So the idea is not to use the face image to make the filter. To start with the face image, you change it. For example, you could convolve it with some random mask, or you can shuffle the pixels randomly. And how do you decide how to shuffle? You need a password or something else that tells you how to shuffle it. And this is going to be, sometimes some people say, but you told me I don't need any passwords if I use biometrics. Wasn't that the first slide you showed? Yes. But unfortunately, we haven't come up with a better mechanism here yet. Some people say, don't use the password, use fingerprints. This is face, this is fingerprint. So you could do some other things. But anyway, to make the main idea clear, you just have to randomize it. Now this is the image from which you make the filters, not this one. So if this is lost, the template is lost, you just change this. Right? And so test time comes, you use the same PIN or password, you do the same random thing, and you correlate this encrypted test image to the encrypted template, and we can show theoretically that there is absolutely no loss in peak to side lobe ratio. Okay? You get equally sharp peaks for the right people. So this is what the authentic person looks like, that's what the imposter looks like. You can't tell anything, but here is the correlation of the authentic using this random kernel. If it matches, you get equally good peak. If you didn't use the encryption, you get the same peak. So by using the encryption, we didn't lose the peak. It's equally strong. If I get an imposter to come in and play against this filter, I still don't get a good peak. If I look at the filter made from one random kernel and bring the authentic but convolve it with a different random kernel, this is what you get. They won't match. Okay? It's a very simple idea, but you need to bring in some of these for biometrics to really be useful. So the last thing I want to talk about is encryption. That is, many times you want to store long keys, like 128-bit encryption key or something like that. So how can you do that? One way to use biometrics for that is you have a biometric test sample, you have stored one, you match them, and you say, yeah, it's an authentic or an imposter. If it's a, I don't know what yes means, authentic or imposter. I guess this means authentic. Authentic is release the key. Imposter, you should not release the key. But the attacker is just going to sit here and ignore all this stuff, and he's going to send a message yes, and you release the key, right? That's how the attacker, that's the weakness in this conventional way of doing it. What would be nice is if the key is somehow stored here in the template directly. So how can we do it? So there are many ways to do it. The way, of course, we're always looking for ways to solve problems using correlation filters, because that's the one thing we know how to do well. So what we said was, what if we can design a correlation filter that produces not a single peak, but 4 peaks, let's say, for you. And so I'll design a filter for Hamid that when Hamid's image comes in, actually produces 4 peaks at the output. And the coordinates of those peaks are his secret key. Right? Each of these peaks have coordinates. If it's a 128 by 128 image, each x coordinate has 7 bits of information. 7x, 7y, each peak gives me 14 bits. Right? Now, for when Wes comes, I'll design a filter for Wes that will produce maybe 7 peaks at a different location. That's his key. So we can use them all, we can design them, and when the test comes in, either we release the key, or we can even make a hash of the key and store it. Only if the hashes match, we release the key. Otherwise, we don't even release the key. So you can play with it more. But anyway, let me get to the final results. So we tested it on CMU Pi database, MultiPy, also palm prints. There is a database of palm prints. We tested it on all those. So what I'm showing you is what we call key retrieval failure percentages. This is when the authentic person comes in and trying to get his or her key. What percent of times did it fail, not work? Imposter key retrieval in all our experiments was 0. Never was an imposter able to retrieve the key of an authentic person. Okay? Whereas we do have some non-0% of times when authentic people are not able to retrieve their own key. So this is the number of bits that we're able to store. Basically, how do we get more bits? We have more peaks. You have to have more peaks to get more bits, because each peak gives you, it's not directly proportional. I mean, it's a function of the number of peaks, but not directly proportional, because I also have to know which peak should be the first set of bits, which peak should I have the second set of bits. So I need to store that information also somehow into the peak location itself. Okay. Also, these peaks will not always be in the exactly right position. So we use a little bit of error correction coding to allow for some errors in that. We also make sure that the peaks are not very close to each other, because then they will start looking like a single peak. So once you put all of it, it isn't exactly this many peaks times 14 bits all the time. So, but anyway, we are able to get much higher than 128 bits. 128 bits is like a holy grail in most of these encryption systems. We can do a lot better than that. And some databases, this is the CMU Pi database with the lights on, without the lights on in the room. This is the MultiPy, this is the palm print. Some are not as good as the others, but you can see Some are easier databases. This is, I use face and palm print. I can split the key into two modalities. Half the key comes from face, other half comes from your palm. Not even half, whatever. You can split between the two. These numbers all get much better. You can also design it so that two different people, what two different? You can have 10 people, key split between 10 people, and as long as any 6 of them are matched, you can get the key back. In this case, only 2. So we pretended that the face images all came from different people, and actually they did. Palm prints are from Hong Kong, and face images are from Pittsburgh, so they're different people. So you can have, you can use you can split the key among different people. You don't have to have, so you and your wife can have a key, and both of you have to be there to get the money. Okay, it's not a good idea. Okay, so sorry for going extra time here. So summary is, I hope I convince you that in spite of the 30 years of history, correlation filters have a bright future because there's still lots of things to do. In spite of my going around and talking about it over and over again, it's only few groups that work in this area. I think there is a lot of, I honestly, my personal opinion is that computer science students don't get exposed to signals and systems. So they don't think about Fourier transforms that much. They do very clever things, but most of them are image-based and feature-driven. I think ECE type of students are in a great position because of it. I think because of the background you get in signals and systems. So I think there's a lot to be done here. And we have lots of other things going on, doing iris from a distance, fusion. Most of the stuff I've shown, even though I said 300 subjects, that's small number in the real world. Indian UID program is 1 billion people. The problem there is going to be not matching, but indexing. Every time an image comes, you don't want to match against 1 billion things. You have to have a much cleverer mechanism of what to match. Indexing. And cameras are cheap. If you're going to do face recognition, why should it be just from one camera? You can put lots of cameras. Then how do you do face recognition? So there's a lot of stuff going on. So thank you very much.
Do you have time for some quick questions?
Yeah.
So you just said that cameras are cheap, but I imagine that computationally some of the things that you do take some time to run. So maybe you could comment about that.
Yeah, so Fourier transforms are much faster than they were before because of all the advances in hardware, but there's still 2D Fourier transforms are still, time consuming. So some of the cleverer ideas I have seen are not to do Fourier transforms at the full image scale. You use these pyramid approaches, like multi-resolution type of approaches. You bring it down to much lower resolution and you do some preliminary Fourier transforms there, and then that tells you a little bit about where is the possible image, and then you go focus on that region more. So blindly applying the full size Fourier transform may not be the good idea. So I think there are still some algorithmic tricks you can bring to bear to help with the speed, but I know that at least I've been told that FFT-based correlations are being used even in ATR type of applications. The speed there is much more critical than the speed in biometrics applications. Most of the time people are okay if it doesn't take more than 2 to 5 seconds. I think if it takes more than 5 seconds, there is an annoyance factor and people will not use the system. So you're right. I think most of the implementations, speed is still the main issue. U.S. visit program, where when people come from outside the U.S. to come into this country, they have to stand in front of the immigration officer and give the, face image and fingerprint. Those fingerprints are actually being matched. Face, I think they're just collecting. Fingerprints are being matched. And nothing really clever about the matching that's going on. What they have are huge number of machines in the back end, and the company that actually built this whole infrastructure to do the matching with it's purely hardware solution. It's an extremely rich company now, the guy who started that. Okay, so sometimes it's kind of depressing because it says the real solution is just throw more hardware at the problem. But I think many of these problems, we have the hardware to solve. But of course, faster is always better.
In some of your algorithms, well, would it be correct to say that there are two parts that are complex? One would be the Fourier, and the other would be the search or gradient descent or whatever you use for doing the search.
The second part is not that hard at all because
so it's always the Fourier.
Yeah, Fourier. We have to do it actually 2 times. We don't have to do it 3 times because the filter is computed beforehand and stored. When the input image, test image comes, you have to do a Fourier transform, multiply, and then do an inverse transform. Those 2 Fourier transforms are the bottlenecks, computational bottlenecks. But looking for the peak, because we really are not trying to sort the entire correlation output. We're mostly interested in where are the biggest values. So that can be done using some thresholding and all that very efficiently. But the Fourier transform, there are a lot of people working on it at CMU. There is a group called Spiral Project. They develop tools where Fourier transform is customized for the hardware. That is, you bring a new hardware, they have tools where it implements the Fourier transform most optimally for that hardware. Professor Jose Mora's group, actually, and Marcus Pushal and others, DARPA-funded project, Spiral, S-P-I-R-A-L. So you have to use those kinds of solutions. But my experience is the MATLAB FFT program, I guess it's called fastest FFT in the West, FFTW or something. That's very good. It's tough to beat that. That's what we use. I think we can get some incremental improvements from it. But any other?
All right. No more questions. Let's thank our speaker.